Welcome back. We're going to consider this time some pulmonary function tests. So we're going to look back again at some of the volumes that are flowing in and out of the lung and how those can change with diseases. And then we're going to start to consider more about the actual composition of the air in the alveoli, because in the next session, we're going to start talking about oxygen transport and talking about the pressure of oxygen and carbon dioxide in the alveoli versus the capillary. And so we're going to start moving in that direction during this session. So pulmonary function tests. So these are again going to be used in helping to diagnose patients with obstructive versus restrictive lung diseases and also monitoring their disease progression. And so one thing that can be measured is the vital capacity, or more specifically the forced vital capacity, which is really what we've talked about before, where you're going to completely fill the lung and then see how much air you can get out so that you get down to the only thing that's left is residual volume. Then there's another thing that can be measured, which is how much you can expire in 1 second. So completely fill your lung and then see how quickly you can get the air out and how much of it gets out in a second. So if you take the ratio of these two numbers, how much can you get out in a second versus how much you can get out over an unlimited period of time, that should, for a normal person, be 80%. You should be able to get 80% of the air out of your lung in 1 second, of the air that you're going to be able to get out of your lung. This is going to exclude residual volume. So in our two types of disease states, then these numbers are going to change. And this should be somewhat predictable that someone with an obstructive lung disease, they have a problem getting their air out, then this ratio is going to be less than 80%. They're going to get less than 80% of their air out of their lung in 1 second. Their vital capacity, their forced vital capacity, is going to be normal. They have a normal lung capacity. In a restrictive lung disease, where they have a problem getting the air in, they have no problem getting it out. So their FEV1 to FVC ratio should be normal. They should be able to get 80% of their air out in 1 second. However, it's the actual numbers for those two capacities that should be different, because they can't, their vital capacity is smaller, and then that means the actual number, the volume for their FEV1 will also be smaller, even though their ratio should be normal. And we're going to see that in this next slide, where Y is going to be this pulmonary function test for a normal person, where here at the beginning you can see they're taking a normal breath. It's about 1/2 liter, so they're breathing in, breathing out normally, and then they're told, okay, inhale as much as you can. And that's where they are right here. And then they're told, okay, breathe out, push out that air as fast as you can. And so and all of your air. And so that's when they exhale, do that force expiratory volume for 1 second. And you can see here after 1 second, they've gotten 80% of their forced vital capacity exhaled. And they have just a little bit left. So their forced vital capacity is, of course, normal, and the FEV1 is normal. Now we can consider someone with an obstructive lung disease, let's say like emphysema, which is this X curve, where here in this example, they're breathing with their lung being more inflated, which is probably going to be a good compensation to help them exhale. So they take a normal breath, and then they're told, fill up your lung, and then they're told, okay, exhale as quickly as you can. And that's when they're pushing and pushing out the air. But you can see after 1 second, they've only gotten a small portion of their forced vital capacity out. And it takes many, many seconds for them to get to that 80% point. So that's going to be typical of an obstructive lung disease. In a restrictive lung disease, curve Z, then you can see that when they do their inhaling, it's a much smaller volume that they're able to bring in. So for instance, they may have scoliosis and they just cannot expand their chest wall anymore to let in any more air. But then when it's time for them to exhale, it's no problem. They can get the air out, and so they're still going to get the vast majority of their air out. But you can see that their forced vital capacity is about 2 liters here, and their FVC should be at about 80% of that. And so if you look at the actual volumes that are being measured, they're much smaller, even though the ratio of the 2 numbers is still 80%. Okay, so we're going to really switch gears now and start to consider what is the composition of the air in the alveoli. And this is an important thing to keep in mind, is that when we're breathing, we are not completely replacing the air in our lung, not even close. And so that's what this is supposed to point out. We're going to have our conducting volume and our respiratory volume, about 150 mils versus 3 liters. And let's say here we have a tidal volume of 450 mils, pretty typical. We're going to bring that into the lung, into the respiratory system, and the last 150 mils, however, is going to fill the conducting volume, which means that only 300 mils of that 450 is actually reaching the respiratory portion that can actually exchange with the blood. So by taking in a normal breath, we have only replaced about 10% of the air in our lung. So that's an important thing to keep in mind, we're only replacing a small portion of our air when we're breathing in a normal breathing like this. And that a lot of what we're doing is filling the conducting volume. That means that we have to really consider how much that conducting volume is, which is also the same thing that we're going to refer to as dead space. So we already talked about what minute ventilation is. That's going to be how much air you're bringing into the respiratory system each minute. So we're going to calculate it using the tidal volume multiplied by the respiratory rate. So we've got 3 different scenarios here. All 3 have the same minute ventilation, multiplying the respiratory rate times the tidal volume. However, we know now that we really need to consider alveolar ventilation. That's what we care about, is how much fresh air is getting to the alveoli. So to calculate that, we're going to take the tidal volume and subtract the volume of the dead space, which in this case we're going to assume is just the same as the conducting space volume of 150 mils. And then we're going to multiply it by the respiratory rate. And so if we do that for scenario 1, we're seeing this person is basically breathing 50 times a minute, but only bringing in 100 milliliters. So it's basically like they're panting. And so in that case, they're only bringing in 100 mils. They're not even filling their conducting space or their dead space. So 0 liters of this air is getting into the alveoli. So the alveolar ventilation is 0. If we have someone that has really a normal breathing pattern of 10 breaths a minute of 500 mils, then their alveolar ventilation, 500 minus 150, which is 350 times 10, is going to be 3,500 milliliters. And then if we have someone that is breathing only 5 times a minute but taking deeper breaths, then we'll subtract 150 from 1,000 and multiply by 5. And so we have actually a greater alveolar ventilation if we're taking deeper, less frequent breaths, so that we can have the same minute ventilation but yet have radically different alveolar ventilation. So it's important to keep that in mind, that minute ventilation does not necessarily mean all that much, that alveolar ventilation is also very important to consider. So we're going to, now that we know the volume of the air that is getting into the lungs or getting into the respiratory portion of the lungs, then what does that mean for the actual pressure of the different gases that are in there? So that's what we're going to start considering, where we know that most of the air that we breathe is going to be nitrogen and only 21% oxygen, and that in the air we breathe, carbon dioxide is very low. We also know that the total pressure is going to be made up of the sum of the partial pressures of the gases, and that means that the pressure of oxygen is going to be equal to the fraction of inspired air that's oxygen times the atmospheric pressure. So since oxygen's 21% of the atmosphere and the atmospheric pressure is 760, that means in the normal air that we're breathing, the pressure of oxygen is 160 millimeters of mercury. Remember that I said that one of the roles of the conducting system was to moisturize air, and so that means that we're adding the vapor form of air, and so vapor form of water, sorry, and so that is going to be, the vapor pressure of water is 47 millimeters of mercury, and so that has got to be subtracted from 760 millimeters of the pressure of atmospheric air to calculate now what the new pressure of oxygen is going to be in inspired air, 150 millimeters of mercury. Okay, so that's the number, the pressure of oxygen in the air once it's entered into the respiratory system before it's been diluted by the air that's already in there. And that's what we're going to start considering. So this is what we've just calculated. We're going to say that we know the pressure of oxygen in the atmosphere is 160. Once it gets humidified, it's going to become 150 millimeters of mercury. We've already said the pressure of CO2 in the atmosphere is very low. Once we get to the alveoli, so we've got this P big A, the pressure of oxygen is going to be much lower, and that's going to be because, remember we said that fresh air is going to be diluted. We're not going to completely replace the air in the lungs, so it's going to get diluted by old air, and the old air is having the oxygen taken out of it continually by the blood. So that's why the pressure of oxygen is going to be lower in alveoli. For CO2, we're going to have a different issue where CO2 is constantly being put into, diffusing into the lung, and so that means that the pressure of CO2 in alveoli is going to be much greater than the almost negligible pressure of the air that's coming in. Then once we look at the pressure of oxygen that's dissolved in the artery or in the arterial blood, that's going to be P little a, or not capitalized. So that's going to be our symbol for arterial blood is PA, P little a. So that's something to keep in mind, because I'm going to be referring to these abbreviations a fair amount. So you can see that the pressure in the arteries is basically matching almost exactly the pressure in the alveoli. And that's true for oxygen and CO2. So we're getting basically complete equilibration between the alveoli and the arteries. And so that means that the pressure of gas in the alveoli is going to be what is going to determine the pressure of oxygen in the blood. And that's what is important. So then that arterial blood is going to be taken to the organs, and the organs are going to take the oxygen and dump CO2 And so you'll see that the pressure in veins of oxygen has now gone down to 40 millimeters of mercury. So a lot of it's been dumped, and that now our pressure of CO2 in the veins has increased from 40 to 46 millimeters of mercury. And we'll be talking much more about these pressures and about how these gases are carried in the blood in future sessions. So we've talked about ventilation, we've talked about minute ventilation, but now we've also considered alveolar ventilation. How much fresh air is getting to the alveoli, because that's what matters. We've also talked about how that means you're going to have to consider dead space, where we've got anatomical dead space, which is the only kind of dead space we've considered so far, which is just the conducting zone of the respiratory tract. Later, we'll consider a little bit areas of the lungs that are not well ventilated or perfused, which is also going to be included when we talk about physiologic dead space. And that's going to occur in just even normal lungs where we don't have perfect ventilation or perfusion in different areas.